Hi guys, we're going to be talking about chapters 1 and 2. There's not really a lot of notes that you need to take if you download the slides. So we'll go ahead and we'll get started. So what do you know about statistics? So typically when we think about statistics, we're thinking about graphs, we're thinking about data, we're thinking about numbers, but there's actually a lot more to it. So it's aggregates of facts, numerically expressed. It affected to a marked extent. These are just kind of examples from the book. My favorite statistics are typically football statistics, so I'm really hoping that we get football back this next fall. In a singular sense, we're looking at a collection of data, clarification of data, presentation, analysis, and interpretation of data. I always love talking about the interpretation of data because depending on the parameters that you're using, it's a really loose definition as to what is statistically significant. So one of the first graphs I'm going to show you, here we have a bar graph. The main difference between a bar graph versus a histogram is that a bar graph actually contains spaces between them and it is typically categorical, whereas the histogram, that actually represents a range of values. So when looking at this, in a past life I used to work for Shore West. So we can go ahead and say, okay, well, Shore West sold the most units in 2016. But is it the best data or the best graph to represent the data? If we were looking at percentages, we could be looking at a pie graph. But when we're talking about numerical data, this is actually a good representation as far as we're looking at here Shore West, First Weber, Realty Executives, Remax, Lake Country Flat Fee, and it goes on for a couple of other ones. So here we're looking at a percentage. So because of the fact that we're looking at percentages, now we're going to be using that pie graph. So here we can see that the majority of people, they find their new home by looking at the internet. Next is going to be your real estate agent. So internet, that could be actually a wide variety of things, but with real estate agent, I'm going to go ahead, I'm going to list that as actual contact. The reason why I say that, I am still in real estate, so I do send emails daily to some of my clients until they figure out which home that they'd like to write an offer on. But is it the best graph to represent the data? Because of the fact that we're looking at percentages and we really limit the number of categories, we could say yes. Typically, we would want to keep it under 6 categories, but due to this, we have the 1% seller, 1% newspaper. They're pretty small percentages, and we don't really want to just put other. Here we have the U.S. real per capita, and let's see, with that, we can see that we have our line graph. This is going to be our trend line right here. We'll learn later on that that's actually called linear regression. And then you can actually see how with the line graph where the U.S. real has increased and decreased over the period of time. When it's talking about what do we need to know in order to understand the graph, so we can kind of piece together this is years or the year. But ideally you do want to have that title there. It's really important that you do have a title for your X and Y axes. You can see that the log of real per capita GDP, okay? So we can actually see that both of our axes are labeled. You can see that this is a period of 20 years, another period of 20 years, and it goes all the way through with a period of 20 years. So these are equal intervals, which is really important. You can also see that this is equal intervals of 0.50. And that's also really important. So you want to keep equal intervals. So if you have the textbook, I believe that this should just say page 26. But for chapter 1, it gives us the example of descriptive statistics. That's the methods for organizing and summarizing information. So descriptive statistics are like basketball statistics, baseball statistics. And then we can take a look at, are either the graphs that were presented earlier, descriptive statistics. So here's the methods for organizing and summarizing. So I would say yes. For inferential statistics, this is going to be making an inference. That's pretty much it. So this is that best guess based on the data that we're collecting. Typically, that's collected from a sample. So when we're talking about the Gallup polls, anytime you look at a Gallup poll talking about the presidential candidates, that's going to be inferential statistics because we're making an inference based on how people are reporting they're planning on voting. But here again, this right here, we're going to talk about this over and over. It's not realistic, economic, nor efficient to actually survey everyone who is 18 or older with voting abilities. So there we're actually going to go ahead and mention that all eligible voters in the country would be considered the population. So instead we survey a snapshot. That's that survey. So when we're talking about descriptive statistics versus inferential statistics, we're looking at the descriptive statistics being this is what actually happened. If we look at the breakdown of the voters after the data has been recorded, that's the percentage right there. That's our descriptive statistics. Our inferential statistics, that's going to be right here. So these are estimates again. So when people are leaving the poll, maybe they're surveying 1 out of every 10 people to try to figure out who might win the election based on that small survey. Here are more examples of descriptive versus inferential. So here you'll actually look at, here's the actual data right here for the bowler. Bowler wants to know his average for the past 12 months. The inferential statement would be that a bowler wants to estimate his chance of winning based on his current average. So the big thing here again, if you take a look, you have a housewife wants to determine how much she spent in the past 3 months. A housewife would like to predict the grocery bills. The politician wants to know the exact number of votes he received last election. A politician would like to estimate. So you can kind of see descriptive is data we already have. Inferential is making a prediction based off of data. For observational studies, we have quite a few of those actually. Researchers are simply observing the characteristics and taking measurements for a simple survey. These are going to be just the tests that are done to see if a pharmaceutical drug actually makes a difference. Another example is that with vasectomies and prostate cancer, we're looking to see of 22,000 men who had a vasectomy, there were 113 cases of prostate cancer. Then we also have the 22,000 men who did not have a vasectomy. Only 70 cases had prostate cancer. So the question here would be, does getting a vasectomy actually cause prostate cancer or not? So for designed experiment, here we're looking at the folic acid and birth defects. So when women are pregnant, does it actually affect whether or not they're going to have a birth defect if she's taking folic acid? So here we study 4,753 women, and we divide them randomly into two groups. I'm going to tell you right now, you are going to hear simple random sample. That is going to be the best way of doing your statistical data. You have to collect a simple random sample. So one group took daily multivitamins. The other received trace elements or a placebo. 13 out of 1,000 women with the multivitamin group had a child with birth defects. 23 out of 1,000 who did not take the folic acid had a child with birth defects. So here we're looking at, well, does folic acid actually contribute to birth defects in women, or does it lower it? We have the U.S. Census. The U.S. Census is pretty much the only time we ever really see a population on mass scale being surveyed. It includes all women, all high school students, all fathers, etc. And it's very accurate data because I don't know if any of you have not turned in your U.S. Census data. They will keep pestering you. I made the mistake one year of forgetting to fill out my data, and eventually somebody did come and knock on my door and ask. So, and they were actually working for the U.S. Census. So it is one where they do try to get all the accurate data. However, for businesses to do that, you can see it's negative because it's costly, time-consuming, and impractical to actually survey an entire population. So when we're talking about who you want to sample, we want to look at our overall population. So how do we want to choose who's in our sample? So, for example, would we want to survey a teacher for surgical procedures? I don't know about you guys, but I don't know much about surgical procedures at all. So you want to have it be representative of that sample. So if you're looking at a surgical procedure, you'd want to interview or survey doctors and nurses. So there again is that example. Would you rather survey a doctor or a financial advisor? And then another question is, would you want to take the mean income of California to represent the mean income of all Americans? With the mean income of California, it is significantly higher because of the fact that the cost of living is also significantly higher. So looking at the mean income in California to represent the entire population of the United States may not be the best strategy. I can also tell you that in Texas, there are some parts of Texas where the mean income is going to be very low and maybe at the poverty level. So you just want to make sure that you're selecting people at random, but that still represent your general population. So here's an example of a sample that was taken that could have used a little bit of work. So Literary Digest magazine predicted that Alfred Landon would easily win over FDR in 1936. However, FDR won by a landslide. So what happened? Why did Landon not win? Well, in this case, the survey only surveyed people with cars or telephones. And when we're thinking about 1936, not a lot of people had cars or telephones. It was a very few elite group who did actually have that. Then you're looking at only 25% of the people polled actually responded. So due to the targeted population, they ended up getting a very disproportionate result, and that's definitely misleading. When we get to chapter 5, we're going to be talking about probability sampling. So with probability sampling, you're talking about a coin toss, rolling a die, spinning a color, random number generators. So that's going to be more about probability, where we talk more specifically about dealing a deck of cards or picking out a certain kind of M&M, but it's all probability. An example of simple random sampling with probability is that it doesn't change the odds. So when we're talking about a bag of marbles, we have a bag of 12 marbles all together, 7 purple and 5 yellow. If I pull out a yellow marble and I put it back in the bag, that doesn't change the odds. So when we're talking about without replacement, it changes the odds. So I'll go back to the example of eating M&Ms. If I open up a bag of M&Ms and I pull out a brown M&M and eat it, I've now changed the probability of picking another brown M&M. I've actually changed the probability of selecting any color of M&M because we have one fewer M&M in the bag now. For the random numbers table, I am going to talk about that. That is going to be in table 1 of your appendix. For some of you, you might have the insert at the front of your textbook, but I can tell you that in the appendix in the back of the book is going to be table 1. This is important because I'm going to zoom in here. Say, for example, I want to randomly select 5 numbers. I want to randomly select 5 two-digit numbers. So I'm going to go to this table, and here's 87, 20, 86, 79, and 35. So those would be my 5 random numbers for two-digit numbers. Say, for example, I went all the way down. So here I got all the way down, I selected 10. If I want to select 11, then I'm going back up. So I have 2, 40, 78, 90. And the random number generator, that actually can change. So the table that I have right here is not necessarily representative of the table that's in the back of your textbook. Just like if you have a graphic calculator that allows you to do a random number generator, those are actually programmed to have the same numbers all the time. So when it asks you for what number do you actually want to start on, you can say, I want to start on number 23. So it's going to go into its database and it's going to start you at whatever number is in the 23rd spot for that number generator. So if you do want to take a break, this is a great time to pause the video. If you don't, we're going to keep going. So for chapter 2, we are actually going to be talking a little bit more about different vocabulary and how to use them as well. So when we're talking about a variable, it's going to be something that's changing. So like when you're talking about variable rates at the bank, it means that your rate is going to change at some point in time. If you're looking at a quantitative variable, that's a numerical change. With a numerical change, I'm going to hop down and we are going to say that numerical change can be discrete or it can be continuous. So discrete means that their whole object changes. So if I ask how many students drive cars, I'm actually giving you two different discrete variables. Students, because the number of students is always going to be represented in whole numbers, and the number of cars, that's always going to be represented in whole numbers. If I asked how long does it take students to get to WCTC, that's an example of a continuous variable because that will constantly change. So I'll give you some examples of that in a little bit, but time is always continuous. If you're filling up a bucket of water, that's the water level itself is always continuous. So it's something that's ever changing. The qualitative variable, this is actually going to be categorical. So it's descriptive. When we were talking about the bar graph with the real estate homes, we had categorical data. So we had Shore West, First Weber, Remax. That would be your qualitative variable because we're not assigning them a numerical value. Data is just the value of the variable, so often a set. And an observation is each individual piece of data. So I want you to take a moment and pause the video to tell me what type of data do you think this is going to be? Is it going to be qualitative, which is categorical, or is it quantitative, which is numerical? And then I want you to follow up. If it is quantitative, do you think it's continuous or discrete? So go ahead and pause, take a moment to do this, and then I will reveal the answer to you. When we're talking about gender, I'm going to increase this here. For gender, we are looking at qualitative data because it's male or female. It is our categories. With the marathon time, this is going to be continuous and it's going to be quantitative. So it's quantitative because of the fact that it's a time, which is numerical. It's continuous. All right, I'm going to backtrack on that. But if it's continuous, it's because of the fact that time is ever going, it never stops. So that's why it's continuous. For blood type, that's qualitative again. Because you have A positive, you have B, well, you have A negative, A positive, B negative, B positive. AB positive, AB negative, and O positive and negative as well. So none of those are numerical answers. For household size, this is going to be quantitative. And for household size, we are also going to say this is discrete. And because of the fact, every semester I have someone make a joke about it, but every person counts as a whole person. With tallest waterfall, you have to look at this very carefully. Are we looking at the name of the waterfall, or are we looking at the height of the waterfall? And because of the fact that it says tallest waterfall, we can argue actually that it's either. If we want the height, that is going to be continuous. I'm sorry, not continuous. It's going to be it's discrete. Because the height actually does end. And then if we're looking at the name, it would be qualitative. For your assessment, I do ask for you to give an example of both a qualitative and a quantitative example. And I also ask you to give an example of a continuous versus discrete example as well. So in organizing your qualitative data, you can do a frequency distribution. And so I give the example of let's create a frequency distribution of our class on brown, blue, green, and hazel eyes, and then calculate the relative frequency. So I'm going to go ahead and just kind of make up some numbers here. So I'm going to do, here's brown, blue, green, and hazel. And actually, I'm going to do that this way because it'll be a little bit easier to read when we're going across. So here's the eye color. We have the frequency. And the numbers I am going to make up, I'm going to say we had 10 people that answered this. So we have 3 with brown, 1 with blue, 2 with green. Actually, we'll change blue to 4. And then 1 with hazel. Okay, so that'll give us 10 if we actually total it together. The relative frequency, that's going to be the probability. So you have 3 out of 10, which is going to be 0.3. I'd be looking for that 0.3. For 4 out of 10, again, we're looking for it in decimal form, so it's going to be 0.2. I'm sorry, 4. My brain was thinking about reducing the fraction. You'll realize that sometimes I will do that ahead of time where my brain won't always process it. So I'm going to try to catch my mistakes. For green, you have 2 out of 10. So that's going to equal 0.2. And for hazel, you have 1 out of 10, which is going to be 0.1. So your relative frequency, that's going to be these decimals right here. So with the pie chart, we're looking at the number of people that prefer going to Florida, California, Alaska, Hawaii, and New York for a travel destination. Notice how with the pie chart, we have the chart title. We also have the different states listed. Ideally, what you want to do is create a key to show exactly what numbers go with what, because right now, just looking at this, we don't know what it is. But if you see 28%, 28% is the greatest with Hawaii. So we would want to label that as red. For the smallest, we have New York. So here's New York. So New York is orange. Next smallest is Alaska, so that's going to be blue. And then I'm going to call California teal. I know it's not really teal. And then Florida is going to be green. So you always want to make sure that you have your percents correctly labeled. You want to make sure that you have the key to the side. And you want to make sure, so notice how here we didn't put 9 people for Florida. We put 18%. So with the pie charts, we want to make sure that we are using the percents or the relative frequency as a percent. This is how that would be represented as a bar chart. So we have the exact same, here's our frequency. Here's our relative frequency. And you can see over here, you should still have a y-axis label. So here we would be percent. Or you could put relative frequency. We have our key right here, and we have the travel destination labeled at the bottom. Do not forget, we want the chart title as well. So travel destination would be a good title for this one. For organizing qualitative data, we can use 3 different types of classification. So we can put them in classes, categories, or bins. We can use single value classes, and we can use single value grouping. So we're going to go ahead and talk about what those actually are. So for single value grouping, we're looking at discrete values. They're distinct. So we're looking at discrete values. So we have the number of people surveyed who have household pets. We want to know how many pets do you have. We're representing these as a single value. And then you can have your frequency with the relative frequency. When you're doing this, don't forget, you total everything up. So you have 40 people that you surveyed, and you have 100% when you're talking about the relative frequency. You may on occasion get 0.999 or something like that because rounding doesn't always work out. But if you round it to the nearest thousandth, so again, the thousandth position is going to be 3 decimal spots, you're in pretty good shape. So for limit grouping, what you're looking at here, we're grouping different values together. So if we're looking at a CD and how long does it take to mature, we would look at 40 to 49 days. Well, there are going to be 2 that mature within 40 to 49 days. And then we represent that tally as a frequency and as a relative frequency. So again, you have the 50 to 59, so you have that range of data. You have 40 people again that were surveyed. And if you add all of the relative frequencies together, you will get 100% of the data. Cut point grouping. So the big difference between limit grouping and cut point grouping, here 49 is included. We don't include decimals with this one. So it's going to be your discrete objects again. For cut point, this is where we have more of a continuous decimal. So here again, it says data are continuous. So when we're talking about weigh-ins, here we have from 120 pounds to under 140 pounds. So it's not including 140, but it's including every value between 120 up to, but not including the 140. So you could have 139.33333, and it still is going to be in that first category. For your histogram, I have examples of what each of them would look like. So for our single value grouping, that's going to be the first histogram because you can see that we are looking at discrete values. For your limit grouping, you can see we do have, there's still discrete measurements even though it's a range. And then for cut point, when you don't see that range written down, it's the 4 up to 6. 6 up to 8, 8 up to 10. When it comes to a dot plot, there are a couple of things that you should be paying attention to. You need to title your dot plot. You need to have your horizontal axis with quantitative data. You need to label the horizontal axis as well. One thing I want to point out, this is single value. I've had quite a few students try to put ranges, and that's not correct for a dot plot. You want to make sure that you're actually writing out specific discrete numbers for your dot plot. The other thing I notice students will do, they don't create equal intervals. You have to have equal intervals. So what does that mean? So here we have +2, here we have +2, here we have +2, and you're going to see that it's +2 going all the way across. So that's going to be your interval. Notice how the dots are perfectly aligned. So here I can see I have 1, 2, 3, 4, 5, 6. I have 6 vehicles that have a 31 mile per gallon rating. I also want to point out that these are equal going across when we're looking at the height. So we want to be consistent about the height that we're making our gaps between dots as well. Because when we're looking at, eventually we're going to get to bell curves, so we're going to look and we have this right here, and then, oh, we've got a peak, and then it goes down again. For your stem and leaf plot, so say for example, we're wanting to put the numbers in, so we have 40, so you have the tens position and the ones position. Tens position, ones position. And say for example, I had another 88. The 8 and the 8 do not count every single 88. So we have 88 once, we have 88 twice. So I would add an additional 8 to represent 88. This is something that I do with all of my classes face-to-face, where I would like for them to create a frequency chart, histogram, dot plot, and a stem and leaf diagram using this data. I want you to go ahead and note there are only 30 days here. One got lost over the years. So since I started teaching this course, I'm not quite sure where that 31st temperature went. but we have 30 days here. And what I'd like for you to do, pay attention to the fact that we are not using years. We don't care about these years. We are looking at temperature data. Okay, so we don't care about these years. Expect that this may take you up to 30 minutes to complete. If you feel comfortable with creating the frequency chart, histogram, dot plot, and stem and leaf diagram, then you're good to go. If you do have some questions about it or would like for me to double check it, you may email me what you have and I can let you know if you're on the right track with that. For the distribution set of a data, so that here we were talking about the normal distribution, and you can kind of see that it's bell-shaped. It's commonly referred to as a bell curve. You can see it's symmetrical. One thing that I want to talk to you about is it is symmetrical at 0. And when I talk about 0, I'll go into it more with chapter 6. But when we're talking about at 0, oftentimes I'm going to talk about the standard deviation. And it's going to be symmetric about the, if it's normally distributed, it's going to be symmetric around the mean. It's unimodal, so it means that the number of occurrences, so say for example with the previous data from our stem and leaf diagram, 88 occurs twice. That would be our mode. And then here are examples of bimodal and multimodal distributions. You don't have to know this for any kind of test or homework. I just want to put it out there for informational purposes. We will talk about skewedness. We have the left skewed. Okay, so you can see that since it's not normally distributed, I'm going to put emphasis on it. Not normally distributed. And the reason why I want to emphasize it is not normally distributed is because if you take a look, your mean is not at the peak. Your mode is going to be at the peak. Your median is somewhere between the mean and the mode. So if it's, you have an average that's lower, it's going to be a negative direction. It's your left skewed or left tailed. If the mean is higher, it is right skewed or right tailed. Here's some information on population versus sample distribution. So for the population, the data for every single person in that population, sample data is going to be the values of a variable for a sample of the population. Recall that it is not economic or efficient to survey everyone. The population distribution represents the population again, and the sample distribution is the graph that's going to represent our population. Note that it's going to look similar, but it's not always going to be exact to the population distribution. So here we have some examples. So when we're looking at the population distribution, it's going to be like that. Notice how the graph here is similar, but not quite the same. I love misleading graphs. I know I'm a nerd when I say that, but misleading graphs are all over the place when you're talking about the news or even in magazines. You're going to see misleading graphs. So when we're talking about the increase in home price, you would think that from 1998 to 1999, that home prices have skyrocketed because there's such a huge gap between the blue and the red data. The problem is this graph doesn't start at zero. Because of the fact that this graph doesn't start at zero, we think that it's going to be a huge jump. What you really should be doing, I'm going to back out of there. So what you really should be doing is having your graph start at zero, and then you're putting a break into your graph. So that way you have a visual representation showing you that the graph does not include up to 79,000. The difference is actually quite small. The difference is only 2,000. And when you're talking about the price of homes, that's pretty small. And then for the unemployment rate, you would think that, let me go ahead and see if I can get a better, you think, oh, okay, unemployment is dropping here. Awesome. Unemployment is going up here. And then it's kind of dropping again. But when we're looking at that, again, what we have to take a look at is this right here. There's no break. We have no break right there. So it looks like there's this huge change in unemployment when really unemployment is only varying from 8.8% to 9.2%. I'm sorry, I missed 8.6 over here. So it's 8.6 to 9.2%. So it's not even changing by 1%. Here are some more misleading graphs. If you take a look at this pie chart, you have 63%, 70%, and 60%. That does not equal 100%. For the home sales, if you're actually taking this small home and we're scaling it to that large home, so first of all, is it saying that it's doubling? The way I look at it, I can fit 4 of these small houses into the large house. So did it really quadruple? So using representation with pictures, as far as the scaling's concerned, you really want to avoid that. Notice how there's no value. It just tells us it's homes in 2000 versus homes in 2001. So we don't know how that actually changed. There's actually an amazing article that I saw in the newspaper, and it had the number of COVID cases back in March. And the way that they actually did it, they had the graphs from whatever city it was in. Well, if you're looking at a map of the United States and you're comparing Houston, Texas to Chicago, it's really hard to see the visual difference because of the fact that they do not start at the same axis. So you want to make sure that you're starting your graphs from the same axis as well. And that's it for chapters 1 and 2. If you guys have any questions, please, please, please email me or shoot me a text message. I'm going to go ahead and write my phone number down here again, just in case. So here's my phone number. Please call me Annie. And then if you are emailing it, just make sure that you're emailing it to the correct address. Because again, they have a student account for all instructors. I don't check mine. So you need to make sure that it's not my.wcdc. You have to do my